In our fourth video from chapter 6, we are going to again get two new reactions. First, the addition of a peroxy acid, and then an ozonolysis. Okay? So knowing the products of those reactions from alkenes and their mechanisms will be the important takeaway. First up, the addition of a peroxy acid. Okay? You take an alkene plus a peroxy acid, and the product is an epoxide. Okay? So probably the first time we've seen this functional group, an epoxide. Right, an epoxide is an ether where the oxygen is part of a three-membered ring. Okay? So here's an epoxide right here. See, three-membered ring with oxygen. A peroxy acid is just a carboxylic acid with an extra oxygen inserted. And we take that extra oxygen, transfer it from the peroxy acid to the alkene to form an epoxide. So again, because we're increasing the number of carbon-oxygen bonds, it's an oxidation reaction. So alkene plus peroxy acid, notice the extra oxygen in here to form an epoxide with a carboxylic acid as a byproduct. And this works because that oxygen-oxygen bond in here is relatively weak, so it's easy to break. So keep that structure in mind for the mechanism. Peroxy acid, extra oxygen in a carboxylic acid. A really common peroxy acid that's used for these epoxidation reactions is metachloroperoxybenzoic acid, or MCPBA. So just like I asked you to know 9-BBN from the previous video, make sure you're familiar with MCPBA and the fact that it's used for the addition of a peroxy acid to an alkene to form an epoxide. So with that in mind, what's the mechanism look like? Well, that oxygen that's in our peroxy acid is electron deficient. So it's acting as an electrophile. Because it's acting as an electrophile, it will accept the electrons from the pi bond of our alkene, which the alkene is the nucleophile, just like every other time, causes our oxygen-oxygen bond to break. Those electrons are delocalized, which causes another pi bond from our carbonyl, the C double bond O, to break, pick up a proton. And then as our OH bond breaks, the bonding electrons add to the other sp2 carbon of the alkene. Okay. So here's another concerted reaction, right? Just like the hydroboration part of a hydroboration oxidation. Everything happens at once. Concerted, everything happened at the same time. So that was listing them out step by step. So what's going on here? Okay, first arrow is this one right here. Okay. The alkene is acting as a nucleophile. So ignore that arrow for a second. The very first step, the alkene is acting as a nucleophile. The oxygen is acting as an electrophile. So the electrons attack the oxygen. That causes this bond to break next. Okay. That bond breaks and moves the electrons over here to form a C double bond O. That's what's present over here. That carbon can't have 5 bonds. Never have carbon with 5 bonds. So while these electrons move over and form that bond, at the same time, this bond breaks and picks up a hydrogen that's forming this part. As it picks up the hydrogen, these electrons then again act as a nucleophile to the carbon that has a delta positive while this is all going on. So we form a bond here in that attack and form a bond here in that attack. That's how we get the epoxide. And the carboxylic acid is a byproduct. But notice in the carboxylic acid, what was previously the OOH of the peroxy acid becomes the double bond O, and what was previously the C double bond O, the carbonyl, becomes the COH. Okay. And we form an epoxide. Not too different from how we formed our cyclic bromonium. Okay. The difference is this is unstable, and epoxide is still not the most stable thing in the world, but it's a little bit more stable because it doesn't have the positive charge here, like we did with the cyclic bromonium. Yep. So the mechanism is a little bit of a challenge, but predicting the products is easy. You see MCPBA, you know what's formed. Break the alkene, draw 2 bonds to oxygen, and you're done. Yep. Form an epoxide. That epoxide does give us a new functional group, and we need to know how to name it. So just a quick little section here on nomenclature. Yep. The common name is just done by taking the name of the alkyl group, the common name, and saying oxide at the end. There's two ways to name them systematically. The first one is considering that three-membered ring with the oxygen to be called oxirane, assigning oxygen position 1 and naming everything else as substituents. But that's not really used all that often. Number 2, why I bolded it here, is the one that's really common. Name it like you would name an alkane with your parent chain, but then just use epoxy as a prefix plus numbers to tell you which 2 carbons the epoxide is attached to. So that's what I'm talking about right here. 2,3-epoxybutane, 1,2-epoxybutane, 1,2-epoxy-2-methylpropane. Just name it as a substituent, including both carbons where the epoxy group is attached to. One right here for practice. I recommend you pause the video, try and get the name. And hopefully you came up with 2,3-epoxyhexane in this situation, 2,3-epoxyhexane. So that's first reaction, addition of a peroxy acid to an alkene to form an epoxide. We finished the video with the next reaction, ozonolysis. And what an ozonolysis does is it cleaves the double bond, right in half, and puts an oxygen in each place. So the double bond that was in the alkene is replaced with 2 double bonded oxygen. We do this by treating the alkene with ozone, O3, at low temperature, and that breaks both the sigma and the pi bond, which is why you've got to keep track of the ozonolysis, because it's the only one from chapter 6 that breaks the sigma bond as well. All the previous reactions just broke the pi bond. Again, increasing the number of carbon-oxygen bonds, so this is considered an oxidation reaction, specifically what's called an oxidative cleavage. It's an oxidation reaction, and it cleaves the reactant into 2 pieces, right? Think like a meat cleaver, cuts it in half. This is our structure of ozone that we'll be considering for the reaction, okay? Notice because of those dipoles, it can act as both a nucleophile and an electrophile. What's the mechanism? We've got the electrophile serving as the doubly bonded oxygen at the end. That adds to 1 of the sp2 carbons, right? Alkene acting as a nucleophile. There's our electrophile. But the ozone is also acting as a nucleophile with a negative charge at the other end. After that first step, we form a product that's known as a malazonide. Okay? That has 2 OO bonds, so it's not exceptionally stable. So it rearranges to form an ozonide. What's it look like? Nucleophile here, attacking the electrophilic oxygen. Electrons move over. Nucleophilic oxygen, we form our malazonide. Okay. Then it rearranges, and notice the bonds shifting around. This bond breaks, moves over to form a CO double bond. This bond breaks, moves over to oxygen. This bond shifts over to form another CO double bond for this intermediate right here, which again forms an ozonide right here. Can you isolate it? Yes. Would you want to? Not particularly, because it's explosive. So what you do at the end of this reaction, right, is treat it with 2 combinations. Okay? You can either use zinc in acetic acid or this guy right here. It's called dimethyl sulfoxide. Sorry, this is dimethyl sulfide, excuse me. That goes through something that's known as the Crigi mechanism. You don't have to know it because it's a radical mechanism. We don't cover those until chapter 12. Okay? But at the end of the day, take the ozonide, right? It cleaves everything in the middle here, produces C double bond O's in the middle there. That's a new functional group. We've seen it in the past. We haven't talked about them extensively. If you have an alkyl group on each side, it's called a ketone. If you have an alkyl group and a hydrogen, it's called an aldehyde. So depending on what was there to begin with in your reactants, what was on the original alkene, that'll dictate what you get at the end of the day. Ketone, if it's 2 alkyl groups, aldehyde if not. This specifically is formaldehyde. other functional groups that contain that carbonyl group that we've already seen in carboxylic acids. We have already seen it in esters. We've already seen it in amides. So know what you need to get the product at the end. Make sure you know the conditions. You need ozone and low temperature, like I mentioned. So O3, low temperature, -78. You get from a mixture of dry ice and acetone. It's not just a random temperature. Okay, so ozone -78, that gets you your ozonide, and then either dimethyl sulfide or zinc and acetic acid, either one. You need it in a two-step reaction to take your alkene, do an oxidative cleavage right down the middle, and replace them with oxygens to form aldehydes or ketones, depending on what was on the alkene to begin with. That's what you finish with on your aldehydes or your ketones. That makes it really easy to predict the product. We can also, we'll see at the end of the chapter, work backwards. Okay? This is, when you see this type of arrow working backwards, it's called retrosynthesis, a future idea in the course we'll talk about in just a little bit. Right? But if you see aldehydes and ketones, right, take those two carbons, join them together to form an alkene, that's what they were made from. And that thought process of working, like where did these things come from? Okay, this type of alkene, that arrow is called retrosynthesis or a retrosynthetic analysis, something we'll introduce not too long from now. Key takeaways from here: peroxy acid, ozonolysis. Know the reactants, know the products, know the mechanism.